Hello, this is a little bit of an exam review for the second exam in EE 3306 Circuits 2. I want to go over because we were in many ways all over the map the last 5 weeks in what we covered, so I want to just go over with some reminders. I'm not going over specifically low and high pass passive filters because that has been very recent. And so if you watch those recent videos and are working on that homework assignment, then you're good to go. But I will talk about other topics on the exam, and I'll go over some different suggestions of things you might want to look at. So since the last exam, we've talked about several things. The first thing to review is that we did talk about special functions. We talked about step functions and how to represent windowed functions as well as other things using step functions. We talked about impulse functions. Specifically, we talked about the sifting property. In other words, what happens when you have impulse functions integrated with other functions. We looked at the Laplace transform. I will say last year I put minimal questions on the exam over the Laplace transform. I have not made out the exam yet. So I don't know the level of questions on Laplace transform that will be on the exam, but I'll try to let you know if I have that ready in time. Also, using the tables and properties, definition and finding a transform through integration. The inverse Laplace transform, also probably minimal questions here. How to use the table, what are partial fraction expansion techniques. Once again, the exam won't be incredibly lengthy. Like, we're not going to have like a 12-hour exam. So, there will be a limit on how long and complicated some of these problems can be. On the other hand, because it is not an in-class closed book exam, it does have to be more difficult and more challenging than a closed book in-class exam. So I have to kind of thread the needle there to be sure that I assess that you really have understood what you need to understand, as well as being sure that you have time to do the work. So with additional topics, we talked about just rational functions in the S domain. What is the definition of pole and zero? How do they behave in the time domain? I will comment that this will not be a Proctoria supervised exam. And so obviously you may access MATLAB and the use of MATLAB, particularly if that's helpful to you in partial fraction expansions. In doing a Laplace transform, there will be certain questions that I may ask you specifically to show your work. So obviously I can't stop you from using MATLAB there, but you will need work to back up whatever your answer is. The initial and final value theorem, particularly the final value theorem, is one that we use a lot to assess Laplace transform when looking at circuits and behavior of currents and voltages. Equivalent impedances and sources in circuits in the Laplace domain, how to replace an entire circuit with a Laplace equivalent circuit, how to solve circuits using Laplace, how to find a transfer function for a circuit, and then the more recent things, what do we mean when we talk about an ideal filter? What are the circuits for passive first order low and high pass filters? That would be either the RL or the RC. How to find the cutoff frequency, and sort of what is the definition of low and high pass, when are they used, etc. All right, so let's look at a little more detail. This is a nice summary on the Laplace transform, definition of the Laplace transform, definition of the step function, definition of the impulse function. A functional transform is defined in your textbook as the transform of a specific function. An operational transform defines a mathematical property of a Laplace transform, and this information gives you the tables in which you can find those. In lump parameter circuits, f of s is always a rational function of s. If it is a proper rational function, you can find the inverse transform by taking a partial fraction expansion. If it's an improper rational function, you first have to do long division and get a polynomial plus a proper rational function. If you if you use MATLAB, you can get the numerators and denominators. I may or may not ask you to demonstrate by hand how to do a partial fraction expansion. F of s can be expressed as the ratio of two-factored polynomials. The roots of the denominator are called poles. They're plotted on a complex plane. Now, we didn't really discuss the plotting of poles and zeros on the complex plane, so when I get to that slide, I'll skip over it. Final value theorem basically says that if you have a function of s and you take f of s and let s go to 0 plus in the s domain, that's basically going to give you the final value in the time domain. It's valid only if poles of f of s, except for a pole at 0, lie in the left-hand part of the s-plane. In other words, that means if the roots of the polynomial are either 0 or negative for the real part. Initial and final value theorems allow us to predict initial and final values of f of t from an s-domain circuit. All right, so here is kind of the important part of circuits and Laplace, and that is, given a particular element, current and voltage, in the time domain, how do we transform that into the frequency domain? And so this table illustrates the replacements that you make, and there was an entire lecture devoted to this, so I'll just show this table and remind you that it's important that you understand this. All right, these are some examples that illustrate problems that are similar to problems that I've given on exams before. So this problem just illustrates how, using step functions, we could define this piecewise linear function. Those are shown here, the solution, and I won't go specifically through these. I just want to present this to you. Whether or not you'll have one that is exactly like this, I don't make any promises one way or the other, but the point is you need to be able to understand the concept behind this and basically how you would do it. Here's a couple of questions on evaluating integrals. The goal here is to use the sifting theorem with the impulse function to evaluate these integrals, and so here are the solutions if you want to peruse those. And then here are some examples of Laplace transform examples. So here's a time-shifted exponential, and then here is a series of step functions. So explanation here, first of all, is how to take the transform of that time-shifted function, and then here we have f of t and how to rewrite those step function sums and windows so that you can do the inverse transform more directly. So I'm going to once again leave you to peruse that answer and be sure that you can get that if you work that out. And then finally, looking at some inverse transform examples, and I will say that examples like this, I'm showing these to illustrate for you the technique, and so they are solved in the next couple of slides, and these slides will be provided for you. But these are maybe a little too long for the exam, although once again, this is an open book work at home exam. So what's too long for an in-class exam may not be too long for an exam that you have plenty of time and resources to work on. So here are the solutions for this particular problem. This first one is pretty straightforward. It's partial fraction expansion. The second one, also partial fraction expansion. Here are some, okay. So this is the one that I want to spend a little time on, because one of the things that I need for you to understand is when you look at a rational function in the S domain, by looking at the denominator, we can know the functional form of what it would look like in the time domain. So you almost have to visualize that you're doing a partial fraction expansion. So you would have a 1 over s term, a 1 over s squared term, and a 1 over s plus 8 term. And without doing any of the mathematics, you know that in the time domain, this is going to look like the sum of a ramp, a step, and a decaying exponential. Excuse me. Part B, I know that the solution is going to look like a step from the S, a decaying exponential from the S plus 2, and the product of an exponential times the ramp for the S plus 2 squared. Similarly, you can read the explanations for Part C and Parts D. Okay, my comments here were the solutions for the problems that you just saw. Once again, I will say the caveat that these expressions that A and B are okay for the exam and C and D are too long. That's assuming it was an in-class closed book exam. For an open book exam, I won't make any promises, but as a general rule, I was particularly interested in this kind of question right here. Can you explain to me what the response would look like? And if you do explain what the response would look like, why? What's your rationalization for why it would look that way? All right. The other thing we talked about, the application of Laplace transforms to systems, how we express the transfer function numerator over denominator. Those are polynomials respectively. Here's a typical Laplace function. Here's what it looks like when it's simplified. It's factored into zeros in the numerator and poles in the denominator, and a gain k. The transfer functions basically represent the ratio of an input or of an output to an input in a linear system. Here's an example of a transfer function. Here is an example of a transfer function, of the same transfer function. First, we factor out the constant, multiplying the highest order term in numerator and denominator. We then get this k, or gain, and then notice the highest order term in both numerator and denominator have coefficients of 1. That allows us then to find the roots. And so in this particular example, we have the following factored function. So the question is, what are the poles and zeros? The zeros occur at -5 and -10, and the poles occur at -1, 2, 3, and 4, respectively. So as we talked about before, as long as the numerator is of lower order than the denominator, it's the denominator roots that determine the time behavior of the system. So in other words, is this exponential decay with different time constants? Is it oscillation? Is it decaying oscillation? So it is possible for poles and zeros to be complex. And the next 2 slides give an illustration of what the time domain function looks like for different expressions in the Laplace domain. So this is just a table from your book. When you have a term like a constant over s plus a, that's exponential decay. S plus a squared is exponential decay times the ramp. Distinct complex roots look like a damped cosine, distinct complex roots squared, a damped cosine times a ramp. So because functions in the Laplace domain represent physical systems in the time domain, we can sometimes work with the function in the Laplace domain and in order to find the initial or final value. And this is where we apply the initial and final value theorem. So here's the initial value theorem and the final value theorem. And here is an example of how to apply initial and final value theorems. So I'll let you look over that and make sure you understand it. Once again, this is not me going back over in detail the entire curriculum, just to try to point out the highlights of what you need to remember, because it has been a while since we covered some of this. So here's another example and another example. So 3 examples for you to look at, and even another example. So 4 examples for you to look at of the Laplace, of the final and initial value theorem. Okay, here's our S-domain equivalent circuits. I think at this point the summary is mostly over. Here's a series of steps. This was a previous edition of your textbook. Now they have that nice little menu that they write out where they show you kind of the steps to take that wasn't really a part of the last book, so I had to do my own. Basically, when you convert a circuit to the Laplace domain, in my little method here, first you want to convert all switches to sources with step functions. You want to convert all time domain sources, or functions for that matter, currents and voltages, to the Laplace domain. So if you've got a source that, say, is a step function, you would want to transform the source to the Laplace domain. You replace all capacitors and inductors with their Laplace equivalents, and this may or may not include initial conditions that would come in as equivalent sources. You convert all unknown currents and voltages from functions of t to functions of s. So the one comment to make here is that Laplace circuits are analogous to phasors. They never mix with time. So you either have a circuit in S or you have a circuit in T. You don't ever have the same thing on a single circuit. So here's a classic example of a circuit in the Laplace domain. This is a parallel RLC. In this case, you have everything starts with initial conditions of 0. You open this switch at t equals 0, and you're fine to sketch the circuit in the Laplace domain. Determine if it is underdamped, overdamped, or critically damped. Now, actually, you can do this without fully solving, okay, because we have for a parallel RLC, and I'm not sure that these formulas were given to you in the notes, but they're easily findable in a textbook or anywhere online. You just Google parallel RLC, underdamped, overdamped, critically damped, and you'll get the relationships. I believe in class we did it for series. So given this expression, you actually you can sketch the circuit in the Laplace domain. All of the elements have 0 initial conditions. I'm sorry, my dog's barking. So you don't have to add any initial condition sources, but you do have that DC source, which is going to transform into 24 milliamps over S once that switch opens. So that's what the circuit would look like. The source would go to 24 over S times 10 to the minus third. The capacitor would go to 1 over S times 25 nanofarads. The resistor stays the same, and the inductor goes to S times 25 millihenries. I may have that on the next page. Yeah, here you go. This is just done without putting the numbers in, just to show you what the circuit sketch is like. Notice the switch was gone. We talked a little bit about RLC circuits. We talked about relationships for R, L, and C, and how to determine whether the circuit is overdamped, underdamped, or critically damped. And then these are just some illustrations of how to work with circuits in the Laplace domain and find I of S. So just going through very briefly, when you have a circuit like this, the first thing you do is you look at the circuit for t less than 0 in the time domain. Assuming it's under DC conditions, this capacitor is an open circuit, and you do that because you have to have an initial condition on the capacitor voltage. You then look at the circuit for t greater than or equal to 0, and you transform everything into the Laplace domain, because now that you know the initial condition on the voltage of the capacitor, you can transform that into a capacitor in series with the voltage source in the Laplace domain. Once you've done that, it's fairly easy to find the current in the Laplace domain, because this is just going to be a single loop circuit with a single voltage source. Okay. Similar here, same approach. You start with t less than 0, so this switch was closed, this capacitor was shorted out, the current was 80 volts over 800 ohms, so that would be the current, the initial current through the inductor. When the switch opens, the source is still in the problem, so you now transform it to 80 over S. The capacitor is just going to be 1 over SC because its initial voltage was 0. The resistor stays the same. The inductor is going to be SL in parallel with a current source pointing down. That is whatever that current was initially divided by S. So these are just some examples of what some circuits look like. that I might ask you to transform. So I've got a couple of others where I just went through and made some comments about what the approach is. Here is another example where you're asked to find the output voltage of S. Then you're asked to determine what's the damping like. If you do a source transformation in the S domain on this current source and this capacitor, then you end up with a series RLC, and you can use our formulas for series RLC to determine the damping type. Okay, here is an example of a circuit that has a source that is not a simple DC source. So when you transform this problem, this source doesn't turn on for t less than 0. It's been sitting for a long time. All the initial conditions are 0. When you transform this, you'll get a complicated function in the time domain. In the Laplace domain. You actually, in the Laplace domain, can find I sub 0 and IL using a current divider once you do the transform on this and get it in the S domain. So that's an approach there. All right, finally, we did talk about transfer functions, and we also talked about filters. So transfer function is always done in the Laplace domain. It's not in the time domain, so it's not little v over little v. We have to change the capacitance to 1 over SC. We have to change the inductance to SL. These become capital V in and capital V out because we're in the Laplace domain. It's a function of S. So you cannot try to do a transfer function on a time domain circuit. I have some people who try to do that every year on this exam, and that's just incorrect. There's no such thing as a transfer function until you transform to the Laplace domain. If you want to do this in the time domain, it's got to be a differential equation. If you want the equivalent of a transfer function in the time domain, you're basically finding an impulse response function, which is a totally different thing. Okay, same here. Remember which one of these arrangements is on these 2 pages, which one are high pass and which one are low pass filters. So you need to look that up and be sure that you can recognize the circuit. Finally here, finding the transfer function of an RLC. Now, we talked this week in this week's lectures, and it is on this week's homework, RLC bandpass filters. That will not be covered on your exam. So hopefully this review, I don't know what else I have here. Let's see what else I've got. I think we're about, I may have just some more like circuit schematics. Yeah, here are some with numbers. Some more with numbers. And here's another circuit where we have a funky input current and we're asked to find the output current and the output voltage. So that's just a couple of examples of some different kinds of circuits that I might want you to mess with on this exam. So hopefully this has been helpful in giving you a review for kind of what to study, because I know there was a lot of material. I know this was a quick summary, but please feel free to address any questions regarding the content of what will be on the exam. I cannot answer questions about the format till I've made it out. I hope to do that tomorrow, but we do have our industrial advisory board meeting, and so it just depends on how much they need me, because I'm the faculty representative there. So just be patient with me. As soon as I know something about the format and can give you more details, like how many questions and how many, I think I've already said we're going to try to do a window and you're going to have like 3 hours. I'm not sure if that's specifically what I said, but I will have many more details about the format of the exam and the time window, and what you'll need in the way of resources should you have MATLAB on, etc. I'll have much more information about that ready this weekend. Otherwise, you now have information on the content that's covered on the exam, and hopefully that'll give you a good solid way to review.